Alright, good morning. Today we're going to talk about Chapter 4, start talking about Chapter 4, and this lecture talks about Section 4.1, Solving Linear Inequalities. Alright, let's take a look back. If you recall, in Chapter 2, we were able to solve fairly easily equations of this type. Alright, so if 2x minus 3 equals 7, if we add 3 to both sides, we get 2x equals 10, and of course x then equals 5. We have what we call a singleton solution. Singleton solution to this equation. Alright, singleton solution means just that. You've got one solution to this equation. There is one value of x which will solve this equation, and that is x equals 5. In Chapter 4, we're going to kind of extend this concept. Well, let's say we want to solve a corresponding inequality. Instead of 2x minus 3 equals 7, let's say we've got 2x minus 3 is greater than or equal to 7. Here your solutions are going to be interval solutions. There are going to be infinitely many values of x that will solve this inequality statement. And we do it much in the same way. I'm going to add 3 to both sides, endeavoring to isolate x on one side of the inequality, get a number on the other side. If I divide both sides by 2 here, I get x greater than or equal to 5. Alright, so typically in an inequality statement you have what we call an interval solution. And this particular statement says x is greater than or equal to 5, which of course means x is bigger than 5 or to the right of 5 on the number line. The equality statement that's included here means the boundary value of 5 is included. If I was to write the solution set formally here, basically I'd put it in brace notation. This means the set of all x values such that x is greater than or equal to 5. And if I graph a solution graph this solution set on my number line, graph solution set, basically I draw a number line. We want all values of x greater than, that means to the right of 5 on the number line. And notice the value of 5 is included in this solution set. I call 5 the boundary value. Alright, so I'll draw a closed-in circle at 5 and shade in everything greater than 5. So we've got infinitely many solutions for x in this inequality statement. I usually put 0 as kind of a milestone. So there is my solution set to this inequality and the graph of the solution set on my number line. Alright, our textbook may sometimes use this notation indicating the closed boundary. The boundary value is included in the solution set with a square bracket. Also notice sometimes the book will use what we call interval notation in these solution sets. This interval notation, most students prefer this brace notation. This interval notation, all this means is we start at 5 and everything to the right of 5, everything to positive infinity is included. I made a little mistake here. Because 5 is included in this solution set, I've got to put square brackets at the 5 boundary. Alright, so this interval notation, I think for publishing purposes, sometimes our book will use this interval notation in the back of the book. Most times I think students and instructors would prefer this brace notation to indicate the solution set with a simple inequality statement. Alright, I'm sure you've seen this topic before in your first course in algebra, so let's just move on and talk about finer points of the game here. Let's do an example. Something a little harder. Solve the following inequality statement. 6x minus 27 is less than 9. Notice this is a strict inequality. Equality is not included in this inequality statement. Alright, I'm going to add 27 to both sides. Again, much like solving equations, I get the resulting statement 6x is less than 36, and divide both sides by positive 6. Of course, the 6's cancel out on the left, and x is less than 6 on the right. Alright, this is my solution set, so I'll just put braces around it and label it solution set. And typically we're asked for a graph of the solution set. Well, less than means to the left of on the number line, as you probably know. So to draw this number line graph, I'm going to put 0 as kind of a milestone. 6 is to the right of 0, and I want everything less than 6. Alright, this is what we call an open set. The boundary value of 6 is not included. 6 is not less than 6. So I draw an open circle at 6, indicating the boundary is not included, but everything to the left is. Remember, less than means left of on the number line. Shade in everything nice and bold, left of 6. Okay? Again, our textbook may indicate this solution set in interval notation. Well, everything left of 6 means everything from negative infinity up until positive 6, and I draw a parentheses here indicating the boundary value of 6 is not included. And our author, you may see in some of these number line graphs, may indicate that instead of the open circle, they'll use a open parentheses indicating the boundary value is not included. And I think most times we'll be satisfied with this brace notation, and probably an open circle would satisfy most for a graph of that solution set. So there's the solution set, and there's the number line graph of the solution set. Alright, so everything we've done up to now is much like solving equations. There is some differences, though, when we start dealing with more difficult problems in this section. Let me sum it up like this. Well, there are some occasions when you reverse the inequality arrow, as I'm sure you recall from first course in algebra. When you add or subtract anything from both sides of an inequality, you leave the arrow alone. Okay? When you multiply or divide both sides of an inequality by a positive quantity, again, you leave the arrow alone. Alright? There are conditions when you must reverse the inequality arrow, as I'm sure you recall, and I'm going to sum it up like this. When you multiply or divide an inequality through by a negative quantity, you must reverse the arrow. Now, this is an easy step for students and sometimes teachers to forget. All right, so we'll do an example of that right now, when you must reverse the arrow. Now let's jump right to an example. Solve the following inequality. (2x minus 9 minus 10x is less than or equal to 3 plus 4x plus 12. Alright, again, the goal is to isolate your x variable on one side of the inequality statement get a constant on the other side, and hence you will have a resulting solution set. Alright, before I start crossing over this inequality symbol, I'm going to simplify within each side. 2x minus 10x, of course, simplifies to minus 8x minus 9 is less than or equal to, and on the right, 3 plus 12 is 15, so I'll write 4x plus 15 on the right. Alright, what shall we do here? Well, I would probably subtract 4x from both sides, seeking to isolate my x variable on the left-hand side, and if you're going to do that, you'd probably add 9 to both sides, and I leave the arrow alone. Because when I add or subtract anything from both sides of an inequality, I leave the inequality arrow alone. Alright, let's crunch things together. I get minus 12x. On the left, the plus 9 and minus 9 cancel out. Less than or equal to, well, here the minus 4x and the plus 4x cancel out, and 15 plus 9 is 24. Alright, and again I leave the arrow alone. Alright, now, if you want to isolate x, you've got to divide by minus 12. And remember, when you multiply or divide through by a negative quantity, you must reverse the arrow. And look at that. Maybe it's good I made that little mistake. Anybody see the mistake? I forgot to reverse the arrow. I've divided by a negative quantity, and when you do that, you must reverse the inequality arrow. Highlight that. Reverse. If it can happen to me, it can sure happen to you. Alright, so now I'll simplify. Of course, the minus 12s cancel out on the left. I get x is greater than or equal to 24 over minus 12 is minus 2. And there is my solution set. My simple inequality statement is my solution set. Alright, this tells me x is greater than or equal to minus 2. And on the number line, greater than means to the right of. So I'll draw 0 as my milestone. Negative 2 is just left of 0. And greater than means to the right of. Notice we've got an equality here, which means the boundary value of minus 2 is included. And shade in everything to the right, all the way to positive infinity, with a nice big bold arrow. Everything to the right of minus 2, including minus 2. So there's my solution set, and there's my graph. Alright, let's try another one. Solve the following inequality statement. Anyway, minus 7 is greater than minus 7 is greater than positive 16/15ths t plus 1. Not always x we deal with. Alright, so goal is to isolate variable on one side, get a number on another side, thus resulting in a simple inequality statement. Alright, what I would probably do here first is subtract 1 from each side and leave the arrow alone. So minus 8 is greater than 16/15ths times t. Alright, notice we've got a fraction to deal with. Don't panic. I'm just going to multiply both sides by positive 15. Get rid of the fraction, right? Well, on the left, again, we leave the arrow alone because we're multiplying by a positive 15, right? Leave the arrow alone. 15 times minus 8 is negative 120. Is greater than, the 15s cancel out here. I get 16t. Alright, now I'm going to divide both sides by 16. And again, we are dividing by a positive, so we must leave the arrow alone. Now minus 120 over 16, I believe that reduces to negative 15 halves in simplest terms, is greater than the 16's cancel out here, and I get t on the right. Now, sometimes students have trouble reading these inequality statements right to left. We usually read left to right, of course. But I claim this is a fine statement for your solution set. You've isolated the variable on one side, you've got a constant on the other, with an inequality statement in between. Now, how do I interpret this? This tells me minus 15 halves is greater than t. Does not that also mean t is less than negative 15 halves? T is less than minus 15 halves. Everybody okay with that? Be sure you can read these inequality statements left to right and right to left. T is less than minus 15 halves. Okay? Maybe write that. If I'm taller than you, you're shorter than me. If minus 15 halves is greater than t, that means t is less than minus 15 halves. And less than means left of on the number line. So my number line graph can look something like this. Minus 15 halves. Actually, it's negative 7.5. But we don't like mixed numbers here. So less than minus 15 halves. Well, again, I draw an open circle. There is no equality statement included here, so it's a open set. Boundary value is not included, so I'll draw an open circle at minus 15 halves. Shade in everything less than, and less than means to the left of, and there is my graph. So here is my solution set, and here is my number line graph of this inequality solution set. Okay. Alright, up the ladder we go. Let's get another screen. Solve the following inequality statement. 2/3 times x plus 2, more fractions, is greater than 4/5 times x minus 3. Well, what's making this a little more difficult is you've got x variables trapped inside parentheses statements. So we're going to have to do some algebraic manipulation and get rid of these parentheses to free up those variables on both sides to combine. Again, the goal being to isolate variable on one side of the inequality statement. Of course, the first thing I want to do is get rid of these fractions. If I multiply both sides by the LCM of 3 and 5, these fractions will go away. Well, what's the LCM? The least common multiple of 3 and 5 is, of course, 15. So I'm going to multiply both sides by 15 and leave the arrow alone, because 15 is positive. Now I can cross cancel. 3 goes into 15 5 times, and 5 times 2 is 10, times the remaining factor x plus 2. And I'll leave it just like that. I'll deal with the rest later. On the right hand side, 5 goes into 15, cross canceling 3 times, and 3 times 4 is 12, times the remaining factor x minus 3. Alright, now of course I'm going to multiply through on these parentheses statements on both left and right. And you have to apply your distributive law. 10 times x is 10x, plus 10 times 2 is 20 on the left hand side, is greater than on the right. Similarly, applying distributive law, 12x minus 36. Alright, I suppose now you've got a decision to make. If you want to subtract 12x from both sides, you'll end up with x variable on the left, which may be easier to read, but you'll have a negative coefficient in front of the x, and you'll have to remember to reverse the arrow when you divide through by a negative. If I subtract 10x from both sides, I will have a variable on the right-hand side with a positive coefficient, and that may be easier to deal with, but then you've got to remember to read the inequality statement right to left. Alright, I'm going to subtract 12x from both sides. Alright, leaving a residue of x on the left. If I'm going to subtract 12x from both sides, I would then probably subtract 20 from both sides. And again, I leave the arrow alone. When you add or subtract by anything, both sides, you leave the arrow alone. So I'll again end up with a minus 12x on the left is greater than, we get cancellations here and here, minus 56 on the right. Oops, sorry, not minus 12x, minus 2x. 10x minus 12x is minus 2x. Alright, now I'm going to divide both sides, of course, by negative 2. And again, it's easy to forget to reverse the arrow. Make that sharper. Reverse the arrow when you multiply or divide an inequality through by a negative quantity. Alright, the negative 2's cancel on the left. I get x on the left is less than positive 28 on the right. And once I've isolated my variable, I can then put braces around this statement and say this is my solution set. Now I'll draw my number line graph. Less than 28 means left of 28, so I'll draw 0 and a marker indicating 28 on the right of 0. No equality is included here, so it's going to be an open circle and shade in everything to the left. Left of, less than means left of in inequality land, right? Alright, so I'll try to make this as pretty as I can here. Nice bold arrow, so there's no question. We go off to negative infinity, left of 28. Alright, 2 more today. Let's see, I don't believe this is in your homework list, but it is in the upper reaches of the exercises at the end of the chapter. This is number 70 on page 332. Solve the inequality statement. 1/4 times x minus 1/3 is less than or equal to x plus 2. Now, what am I going to do here? I don't want to deal with these fractions, especially if I don't have to. I claim if I multiply both sides, all terms, by the LCM of all my denominators, these fractions are going to disappear with an equivalent statement. I'm going to multiply both sides by 12. Right? And I leave the arrow alone because I'm multiplying by a positive quantity. Now the trick is you've got to apply your distributive law. Alright, so let me do that here. 12 times 1/4 x, well of course 4 cross cancels into 12 3 times, and 3 times 1x is just 3x. Minus 12 times 1/3 is of course 4, is less than or equal to, on the right now, applying my distributive law, 12 times x is 12x, plus 2 times 12 is of course 24. Looks wonderful. Now it looks like the easier ones we did earlier in the section, right? Now again, it's a matter of taste. You want to end up with your variable on the right hand side or the left hand side. I think most students and even most teachers would prefer to read these inequality statements left to right. Well, I suppose you should be able to do it either way. Alright, if I subtract 12x from both sides, of course I'm going to then add 4 to both sides and leave the arrow alone. 3x minus 12x is of course negative 9x. Be careful of signs. The 4 and minus 4 cancels out on the left. Less than or equal to, the 12x and minus 12x cancel out, and 24 plus 4 is 28. Alright, so now I'm going to divide both sides by a negative 9. Again, you want to isolate your variable nice and clean on one side of the inequality. And look at that. I did that on purpose. You must reverse the inequality arrow. And let me highlight that. Because you're dividing both sides by a negative 9. Okay? So I'll simplify now. The minus 9's cancel out. I get x is greater than 28 over minus 9. I think our author would probably absorb that negative sign in the numerator. X is greater than or equal to minus 28 ninths. And you're done. Regarding the solution set, 28 ninths does not reduce. So I'll leave it just like that. X is greater than minus 28 ninths. And finally, a graph of this solution set would look like something like this. Well, any negative number is left of 0. So I'll draw 0 as a milestone and negative 28 ninths somewhere left of 0. And greater than means to the right of. And equality means the boundary value is included. So I draw a closed-in circle at minus 28 ninths, indicating the boundary. And shade in everything to the right all the way up to positive infinity. Solution set and number line graph of solution set. Alright, one more. We'll call it a day for this section. And this is from your homework list, I believe. This is number 63. Also on page 332. X minus 7 over 2 minus x minus 1 over 5 is greater than or equal to minus x over 4. Alright, lots of fractions here, and again, I don't want to deal with the fractions. I can multiply by the least common multiple of all these denominators and get rid of these fractions. Well, what's the LCM of 2 and 5 and 4? I believe it's 20, is it not? So I'm going to multiply both sides by positive 20. And of course, you've got kind of a nasty application of the distributive law then on the left-hand side. Alright, let me do 20 times x minus 7 over 2 first. Now 2 cross-cancels into 20 10 times, right? So 2 goes into 20 10 times what? Well, times the numerator, x minus 7. So I'll wrap that in parentheses and I'll work on that later. Minus 20 times x minus 1 over 5. Well, 5 cross-cancels into 24 times. 4 times the remaining numerator, x minus 1, I'll worry about that in a minute, is greater than or equal to, and here 4 goes into 25 times, 5 times minus x, of course, is minus 5x. Alright, so beautiful. We've got an equivalent statement with no fractions now. Of course, I need to perform these indicated multiplications to free up the x variables to combine. So 10x minus 70 minus 4x plus 4, be careful of those signs, is greater than or equal to minus 5x. Of course, it's always best to combine within sides before you start crossing over both sides of the inequality. So 10x minus 4x is, of course, 6x. Minus 70 plus 4 is minus 66, is greater than or equal to minus 5x. So now it reduces to a easier problem we did today. Let's see, I would probably add 5x to both sides. Leave the arrow alone. Add 66 to both sides. Leave the arrow alone. When you add or subtract an inequality through, you leave the arrow alone. So you get 11x, 66 cancel, greater than, minus 5x and 5x cancel, 66. So 11x is greater than 66, and of course if I divide both sides by 11, positive 11, leave the arrow alone, x is greater than or equal to 6. So there is my solution set. And greater than 6 means to the right of 6. Greater than means to the right of, in terms of number line graph. Equality is included here, so the boundary value is included here. I'll close that dot in to indicate that. And all real numbers to the right of 6 solve this inequality statement. So there's my solution set, and there's my graph of solution set. Alright, we've done 5 or 6 of these examples, so we'll call it a day. And this concludes section 4.1, Solving Linear Inequalities.